In this section, we're going to start to deal with binary and hexadecimal as two examples of integer representation. We live in a world where we count with base 10. We have 10 fingers, and we use powers of 10 to represent our numbers. So, for example, when you read this number 1,437, if you read it out loud, you have 1,000, you have 4 hundredths, 30 means you have 3 tens, and then 7 means you have 7 ones. And if you deconstruct this number based on the actual digits, right? The 7 is in the ones place. 7 times 10 to the 0, that's really 7 times 1. Right? The 3 is in the tens place, because that's 3 times 10 to the first, that's 10. Right? 10 squared is 100, so you have 4 in the hundreds place, and then you have 1 in the thousands place. Right? And essentially, whatever base we're dealing with, right, each digit represents the number of counts you have of the given base to the given exponent. Okay. Now, most of what we'll do in computer science will be binary representation, although sometimes we'll use base 8, which are octal, or hexadecimal, which is actually base 16. But this basic concept and algorithms, these algorithms work for any bases. So let's say we wanted to deal with a binary string here, or a bit string. Right? A string of bits, a binary digit. If you write binary digit out, and you just take the IT and the B here, that's where the word bit comes from. It's just a binary digit. We have a bit string here, and just like we start from the rightmost digit as 10 to the 0, 10 to the 1, 10 to the second, 10 to the third, we're going to do that here. This first 1 over here is really 2 to the 0 power, or 1. Okay? This next one here is 2 to the first, or 2. This next one here is how many 2 squareds we have. This is how many 2 cubes we have. This is how many 2 to the fourths we have. This is how many 2 to the fifths we have. And this will be how many 2 to the sixths we have. 64. Okay. Let me just clean this up so it's a little easier to read. So the nice thing about doing this in binary is the only choices for binary digits are either 0 or 1. In base 2, you can't actually have the number 2. Right? Just like in base 10, you can't actually have one digit being the number 10. You can go from 0 to none. So in base 8, we'll be able to go from 0 to 7, but we won't actually be able to have 8 written in base 8. Okay? So now the nice thing, getting back to the nice thing about the binary digits here, the binary numbers, are you either have ones or zeros. So you're either going to count the number or you're not. So let's take a look at which ones of these we want to count. We want to have a 1. Let's do that in a different color. We want to have a 1. We want to have a 2, but we're not going to have the 4 because of the 0. We're going to count the 8. We're going to count the 16, but we're not going to count the 38 because of that 0, and we're going to have a 64. Right? So instead of having 1 times 1,000, 4 times 100, and so on, powers of 10, we're going to have 1 times the power of 2, 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 1 times the power of 2. Right? So basically all we have to do is add up the numbers here. 64 and 16, that's 80, 88, 90, 91. This represents 91 in base 10. Okay? Now, this strategy can be applied to basically any base we want. We're mostly going to focus, as I said, on the binary and hexadecimal bases. But just for example, let's do one for base 8 over here. Right? The first digit is going to represent 7 times 8 to the 0 power. Right? The 0 is going to mean we have 0 times 8 to the first power. And this 4 means we have 4 times 8 to the second power. Right? And then we will add all those numbers together just like we did before. Now, I didn't actually put all the pluses here for base 2, right? But we did add them all up at the end. Right? And again, we don't have anything other than addition to do there. Here we have some multiplication and addition to do. Okay? Now, the 0 doesn't really matter there. 8 squared is 64, so we have 4 times 64. This is a times, not a decimal. Let me just rewrite that so it looks a little bit cleaner. 4 times 64 plus 7 times 1. Right? And if we get our calculator out again, 4 times 64, right, 256, plus 7 would be 263. Okay? So converting from another base other than 10 to base 10 is really just about writing out the each digit as the base raised to a different power, moving from right to left. Okay? Mostly you should focus on doing this for binary strings. Okay? Now we also like to go the other way. What if we start with a decimal value and want to get a binary representation? Okay? There's really two ways to do this. One is going to be sort of a more obvious way to do it, is to just kind of deconstruct all the powers of 2. Right? We have 2 to the 0, 2 to the 1, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th. Let's start filling some of these in. 1, 2, 4, 8, 16, 32, 64, 128, 256. If we go to 2 to the 9th, that'll be 512. And that's too big for the number we have. What we really want to do is find the largest power of 2, right, that is contained inside our number. Right? So the number 312 must have 256 in it. Right? So we can start with the 8th digit being a 1, right? And then you started with 312, you're going to remove 256, and that's going to leave us with 56. Okay? So now what we need to do is ask ourselves, are there any 128s in 256? No, so we'll put a 0 in that place, right? This is 2 to the 8th, 2 to the 7th, 2 to the 6th, 2 to the 5th. That helps to label them here. Oops, I fell one short, so it is good that I labeled them here. Do I have any 64s in 56? No, so I put a 0. Do I have any 32s in 256? Yes, I do, so I'll put a 1 there. Okay, now I started with 56, I accounted for 32, so I'm going to be left with 24. Okay. Do I have any 16s in 24? Yes, I do. So I'll put a 1 in the 16. I'll take away that, in the 2 to the 4th, I'll take away the 16, which gives me 8. Do I have any 8s in 8? Certainly I do. And then when I do 8 minus 8, I get 0, which means all the rest of these would have to be 0. So the way I would write this now is I read this from left to right. 1, 0, 0, 1, 1, 1, 0, 0, 0. And you could certainly check this by going the other direction. I have no 1s, no 2s, no 4s. I'm going to have an 8, a 16, that gives me 24. A 32, that brings me up to 56, and then a 256, which brings me up to 312. Okay? So this is one method to do it. It sort of makes the most sense. It is analogous to what we did going in the other direction. It's a little bit tedious. It involves a little bit of work back and forth, but it doesn't really require anything new. There is another way to do this that involves sort of a shortcut using division. Okay? So this is a good way to learn it, because it makes sense and you can sort of reason out what would happen. But there's a more efficient way to do this, and we'll take a look at that other method right now. Okay? So an alternative way to do this is we do sort of the division house upside down. We do 2 into 312. Well, that is going to go in 156 times with the remainder of 0. Okay? 156 and 156 is going to give me 312. I divide by 2 again. Right, that's going to give me a 78 with the remainder of 0. I divide by 2 again. That's going to give me 39 with the remainder of 0. Okay? And I'm going to keep doing this. 2 goes into 39, 19 times with the remainder of 1. 2 goes into 19, 9 times with the remainder of 1. 2 goes into 9, 4 times with the remainder of 1. 2 goes into 4, 2 times with the remainder of 0. Oops, I'm still on my... Alright, let me put that back. This was a 4. 2 goes into 4 2 times finally with the remainder of 0. 2 goes into 2 1 time with the remainder of 0. 2 goes into 1 0 times with the remainder of 1, and then this would be continuing to be 0, 0, 0, 0 all the way down, but there's no point in going that far, right, adding more zeros at the front of the number, and that's why this actually has to be the front of the number and not the back of the number. So we read this up this way, because if you keep dividing here, you would keep adding zeros. We know that if we add zeros at the end of a number, that changes the number, but if I said 0, 0, 9 in base 10, that's still 9. These leading zeros here don't really matter, so we can get rid of them. So this is a little bit more efficient. It's basically just dividing with remainders. Your remainder is always going to be 0, 1 because you're divided by 2, but then you have to remember to read it back this way. So we're going to get 1, 0, 0, 1, 1, 1, 0, 0, 0, which if you look up here is the exact same number. Ultimately, it's up to you which of these two methods you prefer. Just pick one, practice it, and get good at it so that you can make these things consistent. Okay? Now, if we start having really, really long bit strings, it gets a little bit hard and cumbersome to read. So we have something called hexadecimal, which is base 16. And base 16 can really be used to compress long binary strings. Okay? Now, the fact that you're going up to 16, you can still only put one character in for each digit. So once we get to 9, we want to say the number 10, but we can't take up 2 characters with the 1, 0. Right? So we designate the letter A to represent 10, B represents 11, C represents 12, 13, 14, and 15 for F. Okay? So when we see something like this, 4A7, that A really corresponds to 10. We just can't take up 2 places to write the number 10. Now again, we're doing base 16, so this is really 7 times 16 to the 0. This A stands for 10, and that would be 16 to the 1 because it's in the 16 to the first power, and this would be 4 times 16 squared, and then we would add this all up. Okay, so really the only distinction here is that when you start seeing these letters A, B, C, D, or F, each one of those just corresponds to an integer. And these hexadecimal codes get used a lot in graphics with color codes. You see hexadecimal color codes. Okay, so we're going to get our calculator out again just to finish this off. All right, we're going to do 16 squared times 4, right, it's 1,024. This is just 160, and this is 7. Okay, so if we take that 1,024, and we add 160, and we add 7, we should get 1191, right, and that's our hexadecimal conversion to base 10. Okay. Now, one of the reasons we want to use hexadecimal conversions is every 4 binary digits, right, 2 to the 4th is equal to 16. So we can represent and basically compress every 4 digits starting from the right and going left. Every 4 bits becomes 1 hexadecimal digit. Now, I'm missing a 0 here, but adding a leading 0 doesn't really cause any problems. So we sort of think of these as 4 separate bit strings. 1, 0, 1, remember when we count in base 2, it's 1, 2, 4, 8. So 8 plus 2, this corresponds to the number 10, and 10 would be represented by the letter A. Okay, 1, 2, 4, 8, that's just the number 2, and we can write the number 2. 1, 2, 4, 8, that's the number 9, and we can write the number 9. And then 1, 2, 4, 8, 1 and 4 is 5, so we can write the number 5. So each one of these hex digits corresponds to 4 bits, and then those 4 bits can be converted into decimals. Right? So another way you could convert this into base 10 would be to write this out as a bunch of binary digits and then convert that. But I think this will be a lot easier to do because now you only have 3 calculations to do instead of 12, 4 per each. Okay. So again, this is something that'll take some practice. Mostly we'll focus on base 2, and then we'll start to look at how to add and multiply numbers in base 2.